Okay, so we are going to practice sketching these curves on your own. And the instructions could be, graph using A through H. And I'll remind you on the exam what I want for each of those parts. And you guys are going to graph y is equal to sine of x divided by 2 plus cosine x. All right, so go ahead and push pause and we'll see how you do. Okay, so domain restrictions, well, let's see. We don't want the denominator to be 0, but it will never be 0 because cosine only goes from 1 to -1, right? And so since we're adding a 2, it's never going to get down to 0. So our domain is all real numbers. Okay, intercepts. Y-intercept happens when x is equal to 0. Sine of 0 is 0. Cosine 0 is 1, so it's 0 divided by 3, which is 0. So we're going to want to make sure that the point 0, 0 is on our curve. And then the x-intercepts are when this function equals 0, and the function is 0 when the numerator is 0. Function's undefined when the denominator is 0, but it's 0 when the numerator is 0. So we have to think, when is sine x equal to 0? And that's at the multiples of pi, right, as we're going round and around the circle. So 0, pi, 2 pi, 3 pi, 4 pi, and then also reverse, negative pi, negative 2 pi, et cetera, et cetera. So we're going to have an x-intercept at all the multiples of pi, where n is an integer. All right, so we'll have to remember that one. We do have symmetry because we're dealing with sine and cosine functions. We have that periodic function. So the period is 2 pi. So we're going to have to show that in our curve. Okay, so the period is 2 pi. So if we graph this function from 0 to 2 pi, we can just use it like a stamp and do all the other periods after and before. Let's also see if we're an even or odd function by plugging in negative x. So then we get sine of negative x over 2 plus cosine of negative x. Sine is an odd function, so that would be negative sine of x over 2 plus, and then cosine's an even function, so that will just be cosine of x. And then look at this. This is negative sine x over 2 plus cosine x. I just moved that negative sign out front. And so that equals negative y. So when we plugged in negative x, we got negative y. So this is an odd function. So we're going to have symmetry about the origin. So we'll want to make sure our graph shows that. WRT with respect to the origin. Okay, and then you guys found your asymptotes. Let's see. Again, let's go back to our function. We already talked about how we don't have any domain restrictions, so we won't have vertical asymptotes. And then as x goes to infinity, right, these values are just going to keep cycling, right? So our graph is an oscillating graph. It's not going to go off to infinity. So no vertical asymptotes. As x goes to positive and negative infinity, it's just going to oscillate. It's not going to tend towards a line. So there's no asymptotes in our case. So no domain restrictions, and we have a periodic function. So at the infinities, again, it's just going to go through the values over and over again. All right. And now part E, we're going to do the ID test. So we need to know what the critical numbers are so we can figure out where our derivative changes sign, and it's positive and negative. Okay, so to figure out where the derivative is positive and negative, we're going to find the zeros first. Okay, and here's our function. So we're going to take the derivative, we're going to use the quotient rule. So derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. All right, so let's clean this up because we're going to want to find the zeros, so we're going to want to make it as simple as possible so we can find the zeros. So distribute your cosine, minus minus becomes plus. Ooh, I love when I see that. All right, and what do I see? Cosine squared plus sine squared is equal to what? Equal to 1 by the Pythagorean theorem. All right, so again, Pythagorean, x squared plus y squared is 1, cosine squared plus sine squared is 1. All right, so that looks like a pretty simplified function. So now we can figure out the critical numbers, right? We know the bottom isn't going to be 0, so we have to figure out where y prime, oh goodness, this should be single derivative. I get so excited. All right, so y prime equals 0 means 2 cosine x plus 1 equals 0. Okay, so we're going to solve that. Subtract 1, divide by 2. Where does cosine of x equal negative 1/2? Well, several places. Infinitely many places. So cosine is negative over here, where the x is negative. And when it's negative 1/2, that is at like 2 pi over 3 and 4 pi over 3, et cetera, et cetera. So in that one period from, just one rotation, remember we can focus on one rotation and then we can just kind of copy and paste. We're going to be looking at zeros for our derivative at 2 pi over 3 and 4 pi over 3. Okay, so those are our critical numbers in that one period, just in the one period. And of course, it repeats forever and ever and ever. But let's use those critical numbers and figure out where our derivative, these are the zeros of the derivative. So now let's figure out if we're positive or negative. Okay, so what are we looking at? Let's go back to our function so we can work smart and not hard. Okay, so the bottom's always positive, right? Because it's squared. Squared is always positive. So really we want to know, where is cosine of x, 2 cosine x plus 1, where is that positive and where is it negative? Okay, and we can focus on, so it's right here. Those are our intervals we're concerned about. So let's see, let's test something in here. Like we can look at cosine of 0. So, all right. So here we are down here. So it matters, if this is positive or negative, it's going to make the derivative positive or negative. So if we were to plug in 0, right, it'd be 2 plus 1 is positive. There we go. So halfway between 2 pi over 3 and 4 pi over 3, well, let's choose an easy one. Let's choose pi. All right, and then cosine pi is -1. -2 plus 1 is -1. So we're going to be negative. And then finally, after 4 pi, let's choose 2 pi again. All right, and that's just like 0. So we already know it's going to be positive. Okay. So if our derivative is positive, that means f is increasing. Or excuse me, this is y. Y is increasing on those intervals. And then y is decreasing on the space between. Okay. All right. And then with that, we can also figure out the local mins and local max using the first derivative test. Okay, so these are the zeros of the derivative. And notice our function is increasing, and then after 2 pi over 3, it's decreasing. So this looks like a local max. That's the first derivative test. So it happens at 2 pi over 3, and then we're going to want to plug it in. We'll do that in a little bit. And then at 4 pi over 3, that's the zero of the derivative, and our derivative, excuse me, our function is going to be decreasing, and then afterwards you're going to be increasing. So that looks like a local min. All right, and then to find the value, we're gonna plug that stuff in. It's your root 3 over 2 on the top, and then 2 plus -1/2 on the bottom. And then -3 root 3 for 4 pi over 3. Okay, so we kind of just plug in, evaluate our trig functions, simplify. And then when you guys cancel those denominators, you're going to get your ordered pairs. And it might be helpful to take out a calculator and just kind of estimate what those are. According to my calculator, this root 3 over 3 is about 0.6. All right, so that's what I'm going to put it at approximately on the graph. Okay, and then we have the similar ordered pair on the bottom. So here's our local minimum, here's our local maximum. All right, and that was all about the first derivative test. Last thing is we're going to talk about concavity. And that happens when our double derivative is positive or negative. So let's figure out the zeros of the double derivative to figure out where it's positive and negative. All right, so we have this y prime function. And we're glad we simplified it, even though sometimes it takes a little bit longer to simplify. It's always worth it in the long run. And we're going to find the double derivative of this. So derivative of the top times derivative of the bottom minus, where are we? Derivative of the bottom, so take the derivative of the outside function first, times the derivative of the inside function, times the top function. I remembered this time. and then that goes over the bottom squared. And if we square a square, we get a fourth. So squared squared becomes a fourth. All right, so this is a lot, but let's be clever. So look at, I'm noticing all of these similarities. So we have a common factor in the top is 2 plus cosine x. And we also have sine as a factor in both terms. And we have this 2. Whoops, not that one, this one. So I'm going to factor some of that stuff out. So I'm going to factor out the purple negative 2 sine x. I'm going to factor out the pink 2 plus cosine x. And now what are we left with? In the first term, we'd be left with 1 copy of 2 plus cosine x. And in the second term, see, that goes away, we'd have just the 2 cosine x plus 1. So that's not as bad, right, once we factor out everything. And then we have the bottom. Okay, so here we go. So we can cancel out, this is a factor, right? We have 1, 2, 3 factors. So I'm going to cancel this factor right here. So now we have negative 2 sine x. Parentheses, we're going to get 2 minus 1 cosine x minus 2 cosine x. And then on the bottom, we have 2 plus cosine x cubed. And remember, it's hard to keep track of everything we're doing because it takes such a long time at this level that we're at right now. This is the double derivative. We want to figure out the zeros. Okay, we want to figure out where the double derivative is positive and negative. It becomes positive and negative at the zeros. So the function will be negative when the numerator is negative. Excuse me. This is a long problem. I'm starting to get a little loopy. The double derivative will be 0 when the numerator is 0. And luckily, the numerator is already factored for us. So according to the zero factor property, let's see, negative 2, we can divide both sides by negative 2 because there's no variable in it. So this derivative, double derivative will be negative when sine is 0. I keep saying negative, I mean 0. And when 1 minus cosine is 0. Okay, and remember, we're just focusing on the first period, 0 to 2 pi, and then we'll, copy and paste. Let's see, but sine of x is 0 on 0 and 2 pi, right? Wait, let me take that back. There's one more I'm missing. 0 pi and 2 pi, right? The sine is 0 here. And if we add cosine to both sides, we want to know when the cosine is 1. And the cosine is 1 just right here. And on one period, that's 0 and 2 pi. Okay, so those are the zeros of the double derivative. Once we know the zeros of the double derivative, we can figure out the concavity and the inflection points too, okay? All right, so again, the double derivative is this. This is where we ended up. 2 plus cosine x cubed. Well, 2 is the biggest number, right? So 2 plus negative 1 at most is still going to be positive. So the denominator is positive. So it's up to the numerator. If the numerator is negative, the double derivative is negative. If the numerator is positive, the double derivative is positive. So let me write that out. Negative 2 sine x, 1 minus cosine x. And we're just gonna plug in some numbers. And again, because it's just the first period, we can just focus on 0 to 2 pi and then do a copy and paste to get the rest of the graph. So let's choose pi over 2. So -2 times sine of pi over 2 times 1 minus cosine of pi over 2. Let's see, -2, sine of pi over 2 is 1, and then 1 minus cosine of pi over 2, 1 minus 0 is that. So let's see, -2 times 1, negative. It's -2. Okay, and then between pi and 2 pi, we'll go down south, we'll do 3 pi over 2. So plug it into the numerator of the double derivative, because that's what determines if it's positive or negative. So we have -2, sine of 3 pi over 2 is -1, then we have 1 minus 0. So -2 times -2 is +2. The double derivative is positive right there. All right, and then once we know that, it's, the next period is going to have the same symmetry. It's going to go minus, plus, minus, plus, right? And then so plus, minus, et cetera, et cetera. Okay, so on the first period, 0 to 2 pi, we are concave. If it's negative, it's concave downward on 0 to pi. And then concave upward where the double derivative is negative. Positive. Where the double derivative is positive. So there you go. And then since we have a change in the double derivative, we have inflection points. Since it goes from negative to positive to negative to positive, we have a whole bunch of inflection points. Ours happen at, these are the zeros of the double derivative. We're going to have to go back to the function and see what it is. But they happen at 0, pi, and 2 pi. All right, and then what are those points? We have to go back to our original function. I'll write it here. Again, this is sometimes why these problems are a little tricky. We're going back and forth between 3 different functions, right? And now when we're doing the inflection points on the original function. So that's why we're going all the way back. And let's see. Well, all of these values, 0, pi, 2 pi, it all makes the numerator 0. So y is going to be 0 for all of those points. All right, and now we are ready to graph. Okay, and again, we're just going to focus on the first period, and then we have that nice like horizontal symmetry. Okay, so and we can go this way too. Let's start at the top. So close your eyes if this hurts. Goodness gracious. I went too far. Wow, I really went too far. Okay, so the domain is all real numbers. We have intercepts at 0 and then all multiples of pi. So all multiples of pi, we're going to have that x-intercept. Periodic function, it's an odd function. Period is 2 pi. No asymptotes. We are increasing between 0 and 2 pi over 3, decreasing, and then 4 pi over 3 to infinity, and then decreasing between 2 pi over 3 and 4 pi over 3. So I'll make a note of that. All right, we have some local mins and maxes at 2 pi over 3. Oops, goodness, look at, see we go back, self-correcting mistake, 4 pi over 3. 4 pi over 3. So those are our max and mins. And remember, we said this is about really 0.6. So 4 pi over 3, negative 0.6 is the min, 2 pi over 3, and approximately 0.6 is the max, okay? What else? We have some nice concavity, concave downward from 0 to pi, and then after that it's upward from pi to 2 pi, and we have all of these inflection points. Okay, so can we remember all that? Well, let's do this. So we know on this one period, we have our intercepts at the multiples of pi. Okay, so that's easy enough. All right, and then I'm going to divide this into thirds, because if you remember, pi over 3, we have information about 2 pi over 3, 3 pi over 3, and 4 pi over 3. 5 pi over 3, and then 6 pi over 3, okay? And this is what we know, and I'll draw it in various colors. So from 0 to 2 pi over 3, we said we are increasing. Our graph was increasing. From 2 pi over 3, I'll do it in a different color, to 4 pi over 3, we are decreasing. And then again, from 4 pi over 3 to 2 pi over 3, we're increasing, and then after that we repeat. All right, so we're increasing, and then after that we repeat on that period. We also know that the concavity of everything, so from 0 to pi, we're concave down, okay? So we're concave down from 0 to pi. I'll just do that. We'll adjust it after that. And then from pi to 2 pi, we're concave up. So all these things kind of have to intersect, okay? All right. And then we also have some mins and maxes, so let's get that going as well. At 2 pi over 3, let's see, that would be like 0.5, maybe 0.6 would be like right here. 2 pi over 3 and 0.6, there's your local max. And then 4 pi over 3 and negative 0.6 is your local minimum, okay? And all of these points here in pink, those are your inflection points, so that's where the curvature is going to change. All right, so let's put all these pieces together, and I'll do it in blue. So here we are at 0. We're going to increase to the local max, and then we're going to decrease to pi. And then at that point, our curvature is going to change. Maybe look something like this. And now our curvature is going to change. We're going to decrease to the local minimum, and then we're going to increase back up to pi. Oh, I missed it. Let's see if I can do that better. Okay, and there you go. And then after that point, it's all going to repeat, right? It's going to be like a copy and paste. So we can go on and on and on, and then we can go the opposite direction, going like that forever and ever and ever. All right, so these are big problems, right? A lot goes into curve sketching, but this graph is far more accurate than anything that we are able to sketch in pre-calc, and we're able to sketch really crazy functions. We're not limited to parent functions like we were before. All right, we have one more thing to go over in this section. We're going to be talking about slant asymptotes in the next part.